Okay, so we've defined the basic ideas of probability and this idea of decomposing our events into discrete and disjoint sets. Now we just need to do some cleaning up. So there's a few definitions that we're going to need. We're going to talk about, do a couple examples, and then in the second video we're going to back up and then look at what these all imply. So the first thing we're going to need is a definition for something called a random variable. And the idea is it's going to be a variable and it's going to return a number, and the result is going to be due to some randomness. This is a very vague thing, but the important thing is it's going to be something that gives us a number. So for example, suppose I roll a fair six-sided die. I'm going to roll it twice. I'm going to add the two numbers. Right, and that result is going to be a random variable. Okay, so for example, if I roll a 1 and then a 3, the result is going to be the 1 plus 3 or 4. And we would talk about this as an event, and the event is first roll a 1 and then roll a 3, and so the result of that event is going to be 4. And notice we generally use an uppercase Roman letter for that to denote it's a random variable, and we know that there's some randomness involved. But the other thing to note is, what does it input? It inputs some occurrence of something, and it outputs a number. And that number could be anything. Now we're going to need something else. It's going to be something called a distribution function. The idea is, suppose we have the set of all possible things that it could occur. We're going to call that the sample space, and we often abbreviate that as S. And I'm going to assume I can define sets W sub I. And we're going to assume that these things are disjoint. So that means the intersection is going to be empty if I try to intersect two different sets. And I'm going to assume that I can write my sample space as the union of all of those sets. And as we said in class, I have to define those sets. And sometimes in one circumstance you might want to use one set of W's, another circumstance you'll need another set. It's just something you have to do, and we're assuming it's possible. If that's the case, then we're going to define a function m. We're going to call that a distribution function if its value is going to be greater than 0 for any subset of S. M of S equals 1, and the sum over all the W's of M's adds up to 1. Now once we have that, we can now formally define what we mean by probability. And so the idea is this: if given some subset of my sample space, to find the probability that some event E occurs. And again, we're assuming E is a subset of S. And we're going to define that to be the probability of E is the sum over all the Wi that are subsets of E. And it's going to be the distribution function evaluated for that set. Okay, so basically we're just going to add up all the m's over that set. So for example, roll a die. I'm going to return 0 if even, and 1 if it's odd. Okay. Then I'm going to roll again. And again, I'm going to return 0 if even, and 1 if odd. So under this idea, we're going to define y1 as a random variable. It's going to be the result of the first roll. y2 is going to be the result of the second roll. And I'm going to define x to be y1 plus y2. And now under this circumstance, I need to figure out what are the wi's. So I'm going to define w1 to be, first roll is even, second roll is even, w2 is going to be the first roll is even, second roll is odd, w3 is going to be the first roll is odd, second roll is even, w4 is going to be the first roll is odd, second roll is even. Okay. So given that, I can think of it this way. If my first roll is even, or my, y1 is odd, and for each of those cases, I've got w2 is 0, which corresponds to the second roll being even, or the second roll is odd, and that can happen for the second roll as well. Okay. So from this definition, first roll is even, second roll is even. I define that to be w1. First roll even, second roll odd, define that to be w2. First roll odd, second roll even, I called that w3. And then the first roll odd, second roll odd, we called that w4. And in terms of the x, this corresponds to x being 0, this is x equals 1, x equals 1, or x equals 2. Okay? This is a big if. If each outcome is equally likely, then I need the distribution function to add up to 1. Oops, that's w4. And if they're all equal to the same thing, 1 equals 4m, m has to be 1/4. So I can say the probability that x equals 0 is going to be the same thing as probability of w1 is 1/4. Probability that x equals 1 is w2 happens or w3 happens. And that's going to be careful here, m of w2 plus m of w3 is going to be 1/2. and the probability that x equals 2 is going to be the probability of W4 is going to be 1/4. Now notice in this example, if I'm just focused on the random variable, I've got the probability x equals 0 is 1/4, probability x equals 1 is 1/2, probability that x equals 2 is going to be 1/4. These probabilities are different, but the way I originally defined my W1, W2, W3, and W4, I broke it up and defined it in a way where each outcome was equally likely, and then I could use that to figure out what's happening in terms of my x. Okay, so another example. Suppose y is a random variable, and I know the probability that y equals 1 is 1/4, probability y equals 2 is 1/3, and suppose I know that y could be 0, 1, or 2 is my only possibilities. And note that y equals 0, or y equals 1, or y equals 2 is my sample space. That's all the things could happen, but y equals 0, y equals 1, and y equals 2, those three events, we call it W1, W2, and W3, those are disjoint because y can't be 0 and be equal to 1 at the same time. So under that situation, I know that 1 has to add up to m of W1, W2, and W3. M of W1, I don't know what that is, but I know that m of W2 is 1/4. M of W3 is 1/3, which means that m of W1 is going to be 1 minus 1/4 minus 1/3. So that's going to be what, 12 minus 7? Yeah, or 5/12. And I can express this as a table. My possible values for y can be 0, 1, or 2. Probability I get 0 is going to be 5/12. Probability I get 1 is going to be 1/4. Probability I get 2 is going to be 1/3. Okay. So what's going on here? The really important thing is you're focusing first on events that can occur, and asking what's going on. We want some idea of how likely something is to occur. I'm calling that the likelihood. We need to be really careful. I am the one who's constructing these disjoint sets. And so far, everything has been disjoint, and there's no overlap. That's going to change very soon, and we're going to be very careful because in real life, very few things really are disjoint. And this is seems a little artificial so far because we're assuming we can do that, which is a big assumption. Okay. And what do we have? We want the probability that an event happens. It's going to be between 0 and 1 because the way we've defined the probability in terms of those m's, the biggest it can get is m of the sample space is 1. And we're assuming that we're only focused on things that could happen. And the probability that anything happens is going to be 1. I'm going to claim that if E is a subset of F, then the probability that E happens compared to the probability that F happens is going to be less than or equal. So probability E occurs is going to be less than or equal to probability of F. And the question is how do I show that? So the question is why is probability of E less than or equal to probability of F if E is a subset of F? And this all comes back to this idea that we have this decomposition. So we have W1, W2, W3, where S is the union of the WIs, and these things are disjoint. And what does that mean? That means that if you give me E, I can write it as a union of these W's. And now, let me do this. And this is like some W1 union W2 union W3, blah, 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 out to WK. If I have some F,